All right, guys, so now we want to learn about electricity. Electricity is the flow or movement of charge. So electricity is moving electrical charges. And of course, normally that will be the electrons, because those guys can move. Now, in electricity, today we just want to do a little introductory to some of the properties of electricity. So we want to talk about voltage. We want to talk about current. We want to talk about resistance. And we want to talk about power. So we'll just do the definitions and basically show you how to calculate all these four properties, if you will. All right, so voltage is sometimes referred to, or is a lot of times in physics, the potential difference. So you might have heard of voltage as, for example, a 12-volt battery. And basically what that's telling you is the difference between potential, between the positive and the negative, okay, is 12 volts. Potential difference. The difference between the positive and the negative side of the battery is 12 volts. Now, volts is sometimes written as the number of joules per coulomb. And if you recall, joules would be energy, how much energy, divided by coulombs, of course, is how much charge. So the potential difference between a positive and a negative in a 12-volt battery tells you that there is 12 joules for every 1 coulomb of charge. So 12 volts is 12 joules of energy per charge. And since we're talking about potential difference, it would be 12 joules of potential energy divided by the charge. Normally, we base that on 1 coulomb, so 12 joules per 1 coulomb of charge. So in a 12-volt battery, the potential difference between the positive and the negative, okay, tells you that you have 12 joules per coulomb difference. 12 joules per coulomb difference. If both of these had the same potential energy, then the potential difference is 0, and that normally means your battery has died. Okay. Conceptually, for voltage, it kind of tells you how tall is the hill. So voltage kind of tells you how tall is the hill. So think about our potential energy. Remember, as you go up a hill, your potential energy increases. Same thing with voltage. As you move up the mountain, if you will, instead of a mountain, we're talking about electrical charge. As you move that higher, you increase the voltage. Okay? Sometimes it's referred to as how much push. Higher the voltage, the more push on the electrons. That's another good way to think of it. And again, this is CP physics, so we're keeping it kind of basic, if you will. But as we said, it's potential energy. So if you remember potential energy, as you went up the mountain, right, the more potential energy you had. Same thing with voltage. As you increase that potential difference, the higher the voltage, the higher the push on the electrons in this case. Now, the basic equation for voltage is change in voltage. Again, it's potential difference, so it's a change in. And that is the change in potential energy divided by how much charge you have. And again, our units will be volts in this case, capital V, and that is sometimes written as joules per coulomb. So now let's talk about current. Current is amount of charge divided by time. And so that tells you it is the rate of charge. How fast or slow is the charge moving, those electrons? Anytime you divide by time, you're talking about a rate. So current is the amount of charge divided by time. And the units for current are what we call amps. Okay, so current. And current is represented by the letter I. Okay, and it will be, the units will be in amps. So current is Q divided by T, charge divided by time. How fast or slow is that charge moving? And that is the current. So amps are sometimes written as the number of coulombs per second, so charge per second. Higher your current, faster things are moving. That can be very dangerous in your house because if you get too much current going through, things get hotter and then things can catch on fire. So that's just something to think about. But our equation, very simple there, and we're going to relate all these equations to each other here in a second. But your basics for current, charge divided by time. All right, so resistance, another property of electricity. This is just friction. As the electrons move, there will be friction, and resistance is just a measure of that property, how much friction is involved. Resistance is R, and our units will be in what we call ohms. That will be our omega symbol. Okay, so higher the resistance, the more friction you have. The current will slow down. So if resistance goes up, that means your friction is going up and your current will slow down. If you have less resistance, you have less friction, therefore current can go faster. Measured in ohms, so that's probably a new symbol for us, but that's like the upside down or a horseshoe, I guess, an omega symbol there. But resistance is measured in ohms. Now, power is something we've talked about before. It's the rate at which work is done. Work is just another word for energy. Useful energy, I guess, something is being accomplished. So power will be represented by a capital P. As always, it will actually, we've used this before, is watts. So it's all related, even in electrical terms. Power is measured in watts. Our general equation, power is the change in potential energy divided by time. If you recall from previous chapters, that is work divided by time. And so your power ratings on a lot of appliances, you can find that. Again, little tiny electrons can do work. In fact, our society is based on that. All right, so now let's just look at all the relationships for our equations. I kind of gave you some of the basic equations, if you will, but let's look at just how we can put all this together. So one of our basic equations is voltage equals current times resistance. Voltage equals current times resistance. Manipulate that. Current equals voltage divided by resistance, or resistance is voltage divided by current. All right, so as you can tell here, I forgot to hit the record as I did some of these other equations. So power equals current times voltage. And then what I do is I substitute in for voltage, and I get current times resistance, and then power becomes I squared times resistance. Another equation for power is voltage squared divided by resistance. And then here's just a quick review of all our units. So volts, okay, is in volts. Voltage is in volts. Current is in amps. Charge is in coulombs, represented by Q. T, of course, time in seconds. Resistance is in ohms, and then we use our Greek letter omega here. And then power, of course, is in watts with a capital W. So we'll practice some of these. Let me know if you have any questions. But all these are equations for electricity.